of my research. And my wife usually presents this, and then I go up, because she's the one that did most of the pictures. But let me quickly go through how I got to where I am right now. And first, let me thank everyone for inviting me and for coming to this lecture. And hopefully you'll find interesting what I'm going to present. When I moved to NASA to be part of what was called the astrobiology program. So NASA had the idea that they wanted to study life in other planets. So they started a program called astrobiology. So this is a program they made on ABC News about astrobiology.
Are we alone in the universe? For years, astronomers have been listening to the heavens with radio telescopes for the answer. Now, NASA scientists are trying something new, searching here on Earth for what they call extremophiles, life forms that manage to survive in extreme environments. If they can make it in the toughest conditions found on this planet, they might be able to make it anywhere.
What is it that an organism does to adapt itself to live in boiling sulfuric acid or above, or to live in ice, or even well below the freezing point of water?
That was the movie star image.
Into the ocean vents of volcanoes and lowering probes into the boiling geysers of Yellowstone, looking for hitherto undiscovered forms of life. Why?
We want to understand what the capabilities are for life here, so we have a more rational way of approaching the search for life on other planets.
If it is ever found, alien life probably will not look like this, the Hollywood version, but rather like what one sees under a microscope.
Primarily microbial life forms. We have liftoff of
If there is life on another planet, it's thought the nearest place would be Mars.
Mars, being a smaller target, may have had less of the bombardment that went on in the early development of the solar system, and so that life may have evolved there and been transported here. There was one other example in our own solar system, so then the possibilities for life existing in other worlds and other solar systems just becomes that much more believable.
In other words, we may not be alone.
So why is it that NASA is studying algae? Well, first, I want to tell you a little bit about NASA's perspective on things. Now, first, when you think about space, you think about looking towards the Earth. And if you think about putting a person in space, which, by the way, there have been people floating around in space since 14 years or longer. And people right now are circumnavigating the whole of the Earth every 45 minutes or so in this tin can called the International Space Station. Now, what you may not realize is if you were exposed to the space environment without any protective clothing, you would survive for about 15 seconds. During that time, your blood would boil because of the vacuum, and you would die from radiation and exposure to extreme temperatures. But we know how to put people in space. We also know that there's no place to plug anything in up there. In other words, the reason the space station has got solar panels is because you have to have solar panels or you can't have any electricity. In fact, solar panels are an essential part of space exploration. Now, if we envisioned that we were going to someday send people to Mars, shown here, in the artist's conception of an expedition to Mars, we always include microalgae. Let me show you why. If you go to Mars, and we've sent fantastic probes to Mars and taken actual pictures from the surface of Mars. This was a picture taken from Viking. And what you see on the surface of Mars is an incredibly inhospitable environment. If you ever imagine trying to make a colony on Mars, it would be incredibly difficult because you'd have to carry your air that you breathe inside your clothes. You'd have to find water and make food. And under the very best conditions, on the warmest summer day, the temperature at the equator on Mars may be 18 degrees Celsius at your feet. And the temperature at your head would be around minus 40. And the reason is because the atmosphere on Mars is about 1,000th the atmosphere on Earth, and it's mostly made of CO2. And there's just no basis for keeping the air warm, so it's incredibly cold. Now, we would have to cultivate algae or some other plant that's fast growing to be able to maintain the astronauts and to produce oxygen and take up their CO2. And we'd have to have other forms of solar energy generation. And in fact, what this led NASA to develop is a system called life support. And this is what's called a closed life support loop, in which waste from the astronauts is fed into a chemical treatment system, which is then fed into a biological treatment system to make food and clean water and energy, which feeds the astronauts, which feed the waste system, which feed this cycle. And that cycle, called closed life support, is a critical component of space exploration. But look, this is microalgae between 2,000 and 5,000 gallons per acre per year. So when Saeed told us that we should think about biofuels from microalgae, he was referring to the fact that microalgae is not only a great source of biofuels, but microalgae are responsible for most of the fossil oil that we're currently recovering from the deep earth and the deep sea. So what do I mean by microalgae? I'm talking about single-celled organisms that are the fastest growing plants on the planet. They're fast growing because they have only a single cell and they divide. They have no stems, no leaves, no roots. They're just the single cell that do nothing but divide. They're microalgae because they're very small. And this shows you how small they are compared to a human hair. So this is a human hair, and this is a microalgae cell. Now, can we imagine that algae can be used for biofuels? Can we make feasible, scalable, affordable, sustainable, short-duration development? And can we grow microalgae without competing with agriculture for water, fertilizer, or land? And the answer I'm going to pose to you now could be yes. First, we might be able to grow microalgae using our wastewater. Our wastewater is now pumped in many coastal cities offshore. And that represents, in California, between San Francisco and San Diego, these triangles represent the various wastewater treatment plants. And MGD stands for millions of gallons per day. And if you multiply that number times 3.8 or 4, you get to liters per day. So you see, for example, that the city of San Jose is producing 112 million gallons per day. And if you add all these numbers up, you get 1.9 billion gallons a day of wastewater. That's a lot of wastewater. There's plenty of fertilizer in the wastewater, that's secondary treated wastewater, that can grow microalgae. Voila, we have water and we have nutrients. So where can we put these? Where can we put these systems? Well, if you look at a city, and this wastewater, which is now pumped into the bay, could be redirected for doing microalgae growth into these floating bioreactors. And these bioreactors would treat the wastewater because the algae take nutrients out of the wastewater, and the algae would grow using sunlight, the nutrients from the wastewater, and the system would be mixed by waves. So let me show you conceptually. My student did a nice drawing of this. We put an enclosure into the environment just underneath the surface. We put in microalgae that produce oil, and we put in treated wastewater. The system could be made of flexible plastic so that the waves actually move the system so that it mixes, and the algae then would grow within this enclosure. The algae use solar energy, and they take up CO2 to be able to grow like any plant would do, and they produce oxygen. The heat from the sun, which is a problem on land for bioreactors, would be dissipated into the surrounding water, and we can do a process called forward osmosis I'll tell you about later. We make fuels and cosmetics and fertilizer and animal food. And the biggest issue then would be how many of these things do we have to build? Will it be fields and fields of these bioreactors. And what would the shippers say? And what about the fishermen? And what about the recreational boaters and all the other stakeholders? What will they say if we try to use their environment for making our fuel? Well, let's think about the system. The way it's described is we take treated wastewater and CO2 and we use those for nutrients inside our enclosure. The algae that are in this enclosure use solar energy, and the temperature is controlled by the surrounding water. Waves provide energy for mixing, and the algae that grow produce oxygen and take up CO2. The algae inside this system, which has wastewater in it, are freshwater algae. And so there's this gradient between the inside and the outside, which is salt water, that allows us to do forward osmosis. I'll tell you more about that later. But the other thing that happens is by having salt water on the outside, we have a possibility of controlling the algae. What do I mean by that? What I mean is if something happens and we unexpectedly get a leak in one of our systems, say it gets struck by lightning or something we could never have anticipated, the wastewater that leaks out is the wastewater we currently release into the environment, and the algae that leak out are biodegradable. That is to say, the marine life of the environment will eat that algae and the oil they produce. The lipid is biodegradable, and the algae are freshwater algae. So they cannot live in the marine environment, and they'll die and sink to the bottom. Now, we'll make this out of a very inexpensive plastic, something like polyethylene, which is produced at about 40 million tons a year. And it'll be fixable and recyclable plastic. We have lots of plastic. And the system should be amortized over a long period of time to make the cost work. What are the benefits of the system I described? Well, the first benefit is that we're no longer dumping our wastewater into our coastal areas, but rather we're using the wastewater to grow microalgae that are going to clean the wastewater, which will be further cleaned by forward osmosis. So we'll only release clean water into the environment, which will be good for the marine environment. We fix CO2, which will be good for our atmosphere. And we make products like algae, biofuels, fertilizer, food, and other products. Now, the structure that we're going to introduce into our coastal waters will be a large structure because we need a lot of biofuels, and it should be used as well. It could be used to enhance the marine environment or to do aquaculture, growing edible seaweeds or growing oysters or mussels or other invertebrates. We know that if you put something in floating in the environment, there are a lot of fish that associate with that floating structure, which quickly gets stuff growing on the bottom of it. What do we envision for this structure? Here's a picture, an artist's conception of what this might look like offshore. Some kind of a floating structure put in place that has associated with it solar panels to be able to collect energy from the sun. It has wind energy and wave energy, and then the microalgae are producing biomass energy. We're going to harvest the system semi-continuously and pump this material back to holding tanks, as well as taking wastewater that's feeding this microalgae community. The flue gas from either a power plant or a boiler at a wastewater treatment plant, which is producing CO2 that's going into the atmosphere, will be redirected and feed these microalgae. That's the plan. Now, how much more time do I have? I have time. Okay, what we need is a protected bay, and you have plenty of those. We need nutrient-rich wastewater. We need a source of CO2. And we need access to the coastal region and some kind of infrastructure that we could use to build out the system. Where could we work? Well, we've been looking at San Francisco Bay, although the water's pretty cold there. Here's San Diego Bay, it's a little bit warmer. Here's the Gulf of Mexico, Mobile Bay, that's much better. Here's the Chesapeake Bay, much too cold in the winter. But what about Malaysia? In fact, if we zoom out and we look at the region that you're in, this has got to be one of the most ideal places in the world, both because you have warm water and plenty of sunlight, and because you have plenty of protected bays, copious and in fact too much nutrient-rich wastewater, some concentrated sources of CO2, and a land-sea infrastructure system that could very well be ideal for what we need to do. So let me just end by going back to the beginning of my presentation and reminding you that we are the generation that is going to see one of the most important transitions in the history of humanity. That we, in our particular time, given the numbers of people on the Earth, have populated now spaceship Earth to the point where we're using resources at a rate that the resources are becoming limited, and that spaceship Earth is getting smaller and smaller. We are sort of on a threshold between the time that we're hunting and gathering our energy, just as we hunted and gathered our food for a period of time in the early history of our species. But now we've been hunting and gathering our energy for all these hundreds of years, and we now have to start thinking about cultivating our energy in some sustainable way. We have to cultivate our energy in a sustainable way, because if we don't do that, then there's going to be some very serious problems that we're going to confront in the next couple of generations. Not 200 years from now, but in the next couple of generations, certainly in your lifetime, possibly even in my lifetime, we're going to be seeing some very serious consequences unless we prepare ourselves for cultivating our energy in a sustainable way, both in terms of respecting and regulating our use of energy, but also in taking care of our resources and then making it into some sort of sustainable resource. The Omega system is like an ecology of technologies in which the waste from one part of the system becomes a resource for another part of the system. It's a closed life support system, the way I showed you that NASA has been studying closed life support. It's a challenge for your generation and my generation as well. I'm hoping that we will rise to that occasion, and that we remember that we are not passengers on spaceship Earth, but we're the crew. Thank you.